I'm Bhavedhir V. Bharadwaj. Welcome to episode 19 of Genesis of Tomorrow. The following is a conversation about constructor theory, quantum computing and technology, research workflow, and more with Dr. Chiara Marletto, an Oxford researcher and professor and one of the founding minds of the constructor theory. Also, 86.1% of you watching this have not subscribed yet. So if you get even the slightest bit of value from our show, please support us by clicking that subscribe button so that we can keep on improving the quality of the episodes and keep on bringing such wonderful guests over for you. And now without any further ado, let's get right into it. Enjoy and thank you. And yes, we are rolling. Um to warm up into the theoretical aspect, I'd like to ask you what is the most interesting thing that you've been recently working on.
Um, so my background is theoretical physics. I work in the quantum information theory broad area, but I'm very interested in fundamental problems in physics. So I try to use these general tools and methodologies from the quantum theory of information to address a number of different problems at the foundations of physics, especially quantum physics. And I think the most interesting topic that I've been working on recently is developing a new way to discuss and describe mathematically the phenomena that are important and they are necessary for quantum computing in a context where quantum theory does not necessarily apply. So it's a situation where we cannot assume all the properties of quantum systems to be true. But maybe some of the properties of quantum computers are still there. And so we need to develop a language, even at the formal level, to describe a situation like this, because currently the theory of quantum computation really relies a lot on the formalism of quantum theory of quantum physics. So the Schrödinger equation and all the machinery that comes with it. Whereas in these domains that I'm talking about, it could be that not all the machinery of quantum theory directly applies. And the reason why this is interesting is that there are some domains where we don't know whether quantum theory applies or not. So, for example, when we talk about gravity, some people question whether gravity behaves in a quantum mechanical way. So, there are some theories of quantum gravity, but we haven't confirmed them experimentally. So, we don't know whether ultimately gravity is just classical, the way that Einstein's general relativity describes it, or whether it has quantum features. And so, if we want to study the interface between a gravitational system, like the gravitational field, and a quantum system that has a mass and interacts with it, we need to appeal to some of these more general theories where you don't assume the full quantum theory to apply. But you can still assume, for example, that properties of information theory are true, and also some properties of quantum information theory are true. So that's, I think, the broader area that I find most interesting, in which some of my recent works fit. And specifically, I think there is this approach called constructor theory, which is one of the things I'm working on, which is exactly this approach for this kind of proposal to extend the quantum theory computation beyond quantum theory itself.
You did briefly talk about this already in this part of the conversation, but still, what particular limitations in the current framework of physics in general motivated you to build this entirely new system that you call the constructor theory? And also, before that, it would be delightful if you could give a, a breakdown, a fundamental breakdown of what constructor theory is for people who are new to this entire concept.
Yes. So constructor theory is a program, so a research program. You can think of it as a program that's unfolding. So it's not something that's, it's not a theory that's fully formed. I think we are working on it. So we have developed some aspects and applied it to some problems, but it's kind of developing in a way. So there's still quite a lot to do. And the original inspiration for it came from David Deutsch, who is one of the pioneers of the universal quantum computer. So in about 2011, he published a paper where he laid the foundations, the philosophical foundations of this program. And the program, in a very summarized way, says that there's a possibly an alternative way of formulating physics which doesn't use dynamical laws and initial conditions, but it uses just constraints, mathematical constraints about what is possible, what tasks or transformations are possible, what tasks are impossible, and why. And so it's really a different way of formulating physics from the current traditional paradigm that we follow in physics. And it's intended to supplement the current dynamical laws, so it will not contradict them, but it will supplement them and help us making more general explanations and predictions about phenomena that we may not be able to capture at the moment. Specifically, I think David's motivation came from a number of different directions, but one big field is the field of information theory. So to fully bring information theory within physics and explain information within physics, and this is difficult to do just with dynamical laws. And then another domain is the domain of thermodynamics, where we have things like irreversibility, which clashes with the time reversal symmetry of the microscopic laws. And so one hopes to incorporate this phenomenon of irreversibility at a higher level with these principles that state impossibility and possibility of tasks, which may still be compatible with the underlying dynamical laws being time reversal symmetric. And a third direction is the direction of incorporating the physics of life and ultimately the physics of the mind within physics itself, which has been so far difficult to do with simply the dynamical law approach. So I think these are the three big areas which I think constructor theory can help with. And one fourth area is cosmology. This is where the work really is underdeveloped. We haven't done much in that direction at all. But I think in this motivational initial paper, I think David mentioned a number of possibilities in which constructor theory can help with fixing some of these issues about defining the initial conditions for the universe, which is a notoriously difficult problem. And cosmological theories at the moment are untestable or difficult to test, and they're not developed to the same degree that, for example, quantum theory or general relativity are. So that's a kind of a big problem. So these unsolved problems are the main motivations for constructor theory to this is kind of the main reason why constructor theory was proposed. And the name of the theory comes from the name constructor, which dates back to von Neumann. So von Neumann was interested in how to generalize the idea of a universal Turing machine. And specifically, he wanted to have some programmable machine that could emulate living systems in their ability to self-replicate. And so he wrote extensively about the possibility of extending Turing's paradigm to a more powerful machine, which he called a constructor, specifically a universal constructor, that can be described as a universal machine, a programmable machine. It can be programmed to perform all physically allowed transformations. So not just computations. This would be the universal computer, but it's a universal constructor, so it can do more things than just computations. It has this machine has, in principle, the ability to construct physically viable entities out of raw materials, including a replica of itself, which is something that the universal Turing machine cannot do. So we cannot program a universal Turing machine to create a replica of itself, even though we can program it to simulate, I don't know, a cell that's self-replicating. So I think the name constructor comes from Phenomenon, but somehow Phenomenon didn't develop the theory of these machines. He just conceived of this abstract concept, and then he provided with some of his collaborators. This is also some posthumous work that happened after his death, collected in a nice book. They provided an example of a universal constructor within cellular automata, so with the kind of abstract world made of rules that are not always very physical. Somehow, therefore, abandoning the project of discussing constructors within physics. Whereas constructor theory, with its principles that state what transformations are possible or impossible in the real world, so in a way that it applies to our universe, is also to be intended as a theory ultimately of the universal constructor, because these principles are constraints on the repertoire of this general machine. And basically, it's the laws of physics that ultimately tell us what a constructor, universal constructor, can or cannot do. And so studying the repertoire of the universal constructor is the same as studying the laws of physics and understanding what are the tasks that are possible and impossible. I think this is the key intuition behind constructor theory and why it's called that way. And so for any task that is allowed, there is a constructor that is able to perform it to arbitrarily high accuracy. And a constructor is, in our framework, is simply a device that can operate in a cycle and is capable of performing a task repeatedly over and over again. So in a sense, it's much more general than, I guess, what Phenomenon originally envisaged, but it's adapted to this new scenario. Now, the reason, so I think David suggested this philosophical paper back in about 2011, 2012. And what happened is that I was doing my PhD here in Oxford, and I was interested in Phenomenon's thoughts on the self-replicators in the quantum domain. And so I stumbled upon David's work, and actually it turned out that we decided to actually collaborate on this new theory. So what I was interested, I thought the promise of this program was so great that we could apply it to a number of problems. So I thought instead of developing further this general vision of the theory, let's try to apply the theory as it is to a number of open problems. So I think my contribution was to find a number of problems in information theory and in thermodynamics and also in the physics of life that could benefit from this switch in perspective. And so this was really fulfilling and interesting. So part of my PhD and also my postdoc research was focused on this. And now recently this has led to a number of developments that are very interesting, one of which is also a test for quantum effects in gravity. So I think this shows you how the beauty of this work, I guess, is the fact that you can start from very abstract ideas and then see the consequences of these ideas, how they percolate all the way down to actually apply to something that is testable in the laboratory, which is very exciting. And my motivations for developing constructor theory, to go back to your question, are exactly these, that I think on the one hand, there was a way in which the universal theory, the theory of the universal quantum computer, which is the quantum theory of information, helped us understand much better the foundations of quantum theory. So there's this nice interplay between the study of a machine that is actually, in a sense, very applied, but studying it from the fundamental point of view. So study what it can or cannot do allows you to understand better the foundations of quantum theory. For example, issues to do with measurement, issues to do with entanglement, and resources that you can use in order to perform a computation and so on, are very much related to the symmetry of the theory, the structure of the theory itself. And the idea of replicating this scheme, but now bringing it one level up and using now the study of the repertoire of the universal constructor to understand better broader areas of physics, not just quantum theory, but areas which where quantum theory may not apply, as I said earlier, or areas where we haven't really applied physics to its full potential, such as the physics of life and also thermodynamics, and ultimately the physics of the mind. So this is a very bold vision, but I think that's the vision I have in mind, and that's what the broad motivation that pushes me to kind of look into this direction. I think it's very promising.
I'd love to go a little deeper into these individual aspects of constructor theory and your work in it, particularly, starting with the explicit matter of how it tackles the question of how the quantum phenomena or the quantum workings they translate to the classical environment. What has constructor theory got to say about that?
So this is a very interesting question, which is related to the problem of whether quantum theory applies to all scales or whether it breaks down at some level. And I think many illustrious physicists in the past had doubts about whether quantum theory could be universal. Well, Einstein had problems with quantum theory being universal in the first place, but also Bohr and a number of others were concerned about the fact that it may not apply to for example, macroscopic objects. So beyond a certain scale of macroscopicity, if you like, the quantum effects should dissipate. And not only this should be the case for what's naturally occurring. Obviously, we don't see quantum effects directly at our scale. But the idea is that there's really some fundamental limitation that no matter how hard you try in the laboratory, if you wanted to replicate the quantum superpositions phenomena, for example, that apply to the scale of an electron in an atom, supposing you wanted to apply that to recreate that in the lab for a system that is as large as a human cell or larger, um, a cat, for example, that's what Schrödinger was entertaining in one of his experiments, thought experiments. The idea would be that this fundamental limitation puts like a stop to quantum effects, and we don't know currently if there is such a limitation or not. My personal view is that there isn't. So my understanding is that quantum theory is perfectly consistent. It can be applied to any scale object, and however, there are many people who doubt this idea to this day. Roger Penrose is one of the people who actually have been kind of pushing a program of discussing how to modify the laws of quantum theory to describe this collapse of the wave function or state reduction, the way he calls it, that should apply. It should happen at a certain scale. And now the this fact that there are skeptics of the possibility that quantum theory applies everywhere makes it very important to have ways to describe so general rules to make predictions or have formulate explanations that apply even in a context where you are doubting whether quantum theory applies or not. Because in this way, you can then use these principles, such as constructor theories, and apply them to systems that you can actually test in the laboratory. And in this way, the hope is to generate a number of experiments where you can actually test in a real laboratory whether quantum theory does apply to this object or not. And so in this direction, I think the theory of the constructor theory of information, which is something I developed with David early on during my PhD, and then I developed further in a number of directions, is very useful because it allows you to describe a classical system, a system that can contain classical information like a simple bit, and a quantum bit, so a bit that is um, embodied in a quantum system, such as a quantum spin, which can also be used not just as a bit, but also as a vector of quantum information. It allows you to describe these two objects within the same framework. So you don't have to use two different theories, classical physics, for example, classical Newtonian physics for the bit, and quantum theory for the qubit, but you can actually describe the two systems together. And this is useful because in a context where you are trying to test whether an object does or doesn't have quantum features, which is this situation where you are testing whether quantum theory applies to a system or not, it's very useful to have principles and information theoretic principles of this kind that they apply to both classical and quantum objects. And so I think this is a very powerful tool that constructor theory provides us with, which I have applied to a number of problems, especially recently this problem of testing quantum effects in gravity. But you can also apply to a number of other problems that have to do with this issue of whether some macroscopic object does or doesn't have quantum effects. And so this is a very, very promising direction.
Another aspect that I'd like for you to elaborate upon is the how this theory caters to the measurement problem.
So the measurement problem is a broad term that has been used to describe part of these issues that I was mentioning earlier. So they all go under the umbrella of, does quantum theory apply universally? And the idea is that when a measurement occurs, especially when you regard the measurement as occurring by coupling a quantum system that has these quantum features with a macroscopic measuring device that appears to be completely classical. So the question is whether at that point quantum theory should break down in some way. And instead of still being able to describe this situation of measuring a quantum system in the quantum way, so allowing for all the multiplicity of different possible outcomes to be part of the explanation, whether you should in fact choose one of the outcomes to be the one that's being observed as describing reality as it is and forgetting about all the other possibilities. And now the issue here is that the fact that quantum theory obeys Heisenberg's uncertainty principle, which you can also talk about as the superposition principle. So the fact that you cannot, there are some observables that you cannot measure simultaneously with the same device to the same arbitrarily high accuracy. This fact is in direct contradiction with the idea that you can measure all the properties of an object and see them all simultaneously as they are. So in a sense, quantum theory requires us, when it applies to a system, to postulate the existence of entities which you can call observable, quantum observables, or some people call them Q numbers, some other people call them a quantum wave function. These are properties of the object in question, which exist independently of whether they are observed or not, and whose actual value is unpredictable. So when you try to measure them, you can always say what probability you have to observe one outcome or another, but you cannot say that the value, that they have a definite value prior to the measurement. A definite value that can be observed, of course. What they have is that they have a definite value, but this is represented by an object that's not directly observable, and these are these Q numbers that you can so they're quantum numbers. You can represent them as matrices or operators, if you like. And so this departure from the classical intuition that says I have a cup, and this cup is has got a definite color, a shape, a position, a velocity. All of these things I can actually test directly. The values are well defined and I can see them. This idea that I can see all the features of an object directly when I look at it is an idea that we simply have to abandon when we go to quantum theory. And some people, as I said, many of the founding fathers of quantum theory, and also recently, more recently, contemporary physicists have a problem with this, and they find this idea problematic. And that's what the measurement problem really means. So the fact that how can you explain that you do see a definite outcome when you look at the system in question, while on the other hand it's described by this superposition of different values, or it's described by these q numbers and so on. Now, to me, this isn't a problem, and I think there's a school of physicists that thinks that this is also not a problem. So, especially after this was already voiced back in the days of by Schrödinger and Heisenberg and the founding fathers of quantum theory, but it was most precisely formulated by Hugh Everett, who introduced an interpretation of quantum theory which is called broadly speaking, the many worlds interpretation. And this interpretation, which is then declined in many ways, and now currently there are so many different ways of thinking about it that it's not even clear. There are different views between people who think this is a good interpretation. But apart from that, the broad trait that they all have in common is this fact that they regard the act of a measurement as simply the formation of correlations between the system that's being measured and the measuring device. And this description allows you to, in fact, describe both the measuring device and the system that's being measured in a very democratic way. So they're both described within quantum theory. And if you follow it through, you will see that there is no contradiction between this general description, where the measuring system becomes entangled with the measured object. And so, in a sense, it joins the quantum superposition, and it's described completely by quantum theory at the higher level. And the fact that each of us is still seeing one outcome when you perform the measurement, because these two aspects are not really in contradiction; they can coexist. And so, this for me is enough to say that this is a satisfactory description. That just quantum theory can be used to describe a measurement in this very beautiful way, where you regard this simply as an interaction that can create quantum correlations between the measuring device and the object that's measured. And in this way, you also automatically see that there is a beauty of this way of looking at it, because you immediately see that measuring something is the same as copying its values. So you can see the measuring process as a logically reversible transformation, rather than as an irreversible collapse. And I think this is very nice for information theoretic purposes, because you can immediately relate it to computations, because reversible computations are permutations. And there is a beautiful way of regarding a measurement as a copying operation, which is basically looking at it as a reversible computation. And I think this is one of the key ideas that power the idea of quantum information, quantum computing, because if you don't regard the measurement in this way and you try to introduce collapse theories and things like that in the context of quantum computing, you will quickly find a number of contradictions. Whereas if you keep everything nicely, consistently within quantum theory, you start seeing some of these beautiful effects that power quantum algorithms, etc. So in that sense, I think the measurement problem, I don't see it as a problem. And I think we have all the tools to understand it now. So in a sense, it was a problem, but it's been solved now. And largely speaking, I would say quantum information theory helped greatly with that. It provided lots of conceptual milestones to move beyond the measurement problem itself. And I think now constructor theory hopefully provides an extra, step on the ladder to apply some of these tools that the quantum theory information provided in domains where quantum theory may not apply, but you may still have issues with the measurement problem, because you may still have phenomena like quantum superpositions, even though quantum theory is not directly applicable.
On the computational side of things, how do you see the possibility of what all is computationally possible currently in regards to quantum computing? How do you see that being redefined with the advent of so many different and novel approaches uh, that try to understand quantum mechanics fundamentally, but also the technological and engineering innovations and advancements?
Uh, I think that the technology has improved dramatically over the past decades, and in fact, I think that quantum, well, in a sense, the studies of quantum informations, particularly the study of quantum entanglement, has been one of the most powerful engines of this expansion in the context of quantum technologies. So on the one hand, you have things like, for example, quantum cryptography, technologies to, platforms that can implement quantum cryptography, entanglement-based quantum cryptography, for example, which are developed in a sense independently of the existence of a fully functional universal quantum computer, which is something that we're still working towards. Um, and so these milestones, such as quantum cryptography, are things that helped a lot in the early developments of the quantum technologies, because they showed that there were things that you could develop independently, even if you didn't have this fully functional universal quantum computer. And now, recently, apart from this global race to have more and more qubits that you can put together to work coherently to solve number of computational tasks, um, there's also been a huge improvement in the context of quantum sensing and quantum metrology, which are two branches of technology that are needed to develop quantum computing. Broadly speaking, because performing a quantum computation requires one to estimate a quantum state, which requires very, very fine tuned quantum sensing devices. And this has actually opened up a number of really interesting possibilities for fundamental physics, in the sense that we are now able to manipulate more and more accurately objects that have, let's say, a large mass, so large compared to, say, the mass of an electron or the mass of a neutron. So objects that are like a Bose-Einstein condensate, they are 10 orders of magnitude higher in mass than a neutron, for example. And these objects are extremely difficult to manipulate in a quantum mechanical way, but there are some groups around the world that are already doing this, thanks to the development in the technologies that was fueled by the quantum computing effort. So in a sense, the development in the quantum computing direction not only has this great promise of delivering the universal quantum computer ultimately, but I think it has this fantastic um, spin-off that allows us to have tools um, that make us able to really manipulate quantum mechanically objects of increasing mass and sizes. And why is this important? Well, this is important because this goes back to this issue that you asked me about earlier in regard to the quantum measurement problem. So you want to manipulate objects of larger mass in a quantum mechanical way because you want to check whether they can undergo a quantum interference experiment, for example, so whether they can themselves have quantum effects in them. And also, you might want to test with these objects whether, for example, gravity has quantum effects. So one important application of experiments you can manipulate large masses with in a quantum mechanical way is that a mass always interacts with gravity, and by looking at what the mass does in a context where it's behaving quantum mechanically, you can infer some properties of the gravitational field and see whether the gravitational field itself is behaving quantum mechanically or not. So this is an example of a possibility that's brought about by developing quantum sensing, which is very important for quantum computing, but it's really a possibility that's very relevant for the foundations of physics more generally. Like it's a very important question, this one of understanding, for example, if gravity is quantum mechanical or not. And I think we're getting closer to being able to doing that.
Okay. How does your work in constructor theory and in general informs the philosophy of science? Maybe the issues of determinism, causality, free will, all that.
Um, so this is a very interesting theme. I guess one of the philosophical aspects of my work, and I think I quite like it. Find it very interesting. Um, I think the so at the broader level, I think the fact that you can solve some problems that appear unsolvable within a certain paradigm, for example, the paradigm of dynamical laws and initial conditions, simply by changing the way in which you phrase the laws, is a very nice, it's a very powerful concept. And I think this has been um, applied, it's been applied in a number of ways in physics, and it does apply in this case in constructor theory. So there are some problems, such as, for example, these issues of expressing some properties of information theory, some properties of thermodynamical systems, some properties of living systems, which appear really cumbersome to do within the the traditional approach to physics. But as soon as you switch to this other approach, everything comes very elegantly, and it seems almost natural to address these issues. And so this is a first philosophical implications, and I think it's important that we remind ourselves that even if some things are working really well, such as dynamical laws for a very broad set of things, it's still useful and important to try to use different approaches if you find a problem that appears to be very robust and doesn't quite get solved by using the traditional methods. Um, then as you pointed out, I think this idea of causation can be nicely revisited in the context of constructor theory, because with the dynamical law approach, it's difficult to talk about the cause, given that the laws are time reversal symmetric. You can always consider what you regarded as initial condition that caused some later developments in the dynamics of a system. You can always regard those as the causes, but also you could regard just as well the final conditions as the causes, because you can run the laws backwards, and those are actually the final conditions are the things that seem to have caused what happened. And so there is somewhat an ambiguity in the idea of a cause, and that's not somehow it becomes a very difficult concept to use in the context of dynamical laws. However, there is a very clear sense in which, on the other hand, a constructor, a system is a constructor or not for a given task. So it's obvious if you look at a computer, for example, computer is a special case of a constructor, that there's a specific part of the computer which is its tape, if you like, or the memory that's being used to write and compute things. That's a thing that's acted upon. And then there's part of the hardware of the computer which is simply the unchanged, and it's not affected by any of these computations, and it's the thing that's actually performing the computations. And that's the approximate constructor. Why is it? Because it stays unchanged in the ability of causing a computation again. So this distinction between what is a constructor and what isn't in a given transformation is very objective, so it doesn't depend on which point of view you adopt. It's just you have to check whether in a given transformation there is a thing that stays itself, so that doesn't change in some aspect, that it can work in a cycle. So, and that thing is a constructor, and the rest is not. And this distinction is quite is just very easy to spot and to make. And so you can regard the constructor as a cause in a sense. So you can redefine a cause as being a constructor in a given context, and that doesn't have an ambiguity, and it seems very natural to talk about it. It's very appropriate for chemistry, for example, where you have a catalyst that can be regarded as a constructor. It's appropriate for computer science, where you have a computer that's a constructor. It's appropriate for thermodynamics, where you have heat engines which work in a cycle to perform thermodynamical transformations. and so on. Certainly appropriate in the physics of life, where some parts of the cell can be regarded as approximate constructors, etc. So in that sense, that's an instance of how just by changing the perspective, you can suddenly make sense of a concept that didn't make sense in the context of the dynamical laws, but it's very naturally embedded in constructor theory in this new way somehow. So that's another philosophical implication that I find important. And the third important thing, I will just mention three because there are many, I think, but I find these three maybe they're the most interesting ones. So this third important thing is that um, by looking at this idea that I said earlier, that it seems usually in standard physics that objects like computers, heat engines, constructors more generally, are predominantly emergent, they are macroscopic, they are not fundamental. Usually they're not regarded as the physics of these objects is not, it's nowhere to be seen in the standard model, is not this fundamental symmetry of the laws of nature, doesn't seem to be anything very important, is only of concern for maybe engineers or something. That's the kind of traditional view for these kind of objects. So obviously they operate according to the, if you look at the particles that compose a computer, ultimately they have to obey the particle, the particular laws, the dynamical laws that we know. But the computer itself is not regarded as a fundamental object in physics. But actually that's not true. So if you look at certain regularities that underlie the inner working of a computer, so the fact that, for example, some computations are allowed in a given physical system and others are not, that is a fundamental thing. So if you study the repertoire of a universal computer, for example, that is powered by a given dynamical law, you will understand that dynamical law better. And so this is a very powerful intuition. I think it's the intuition that was behind the idea of universal quantum computers. So how people found the idea of a quantum computer, and even more so, this is really deeply seated within constructor theory. And as I said earlier, the hope is that by studying the repertoire of universal constructors, or more broadly, constructors, programmable machines of that kind, you will be able to understand very fundamental symmetries of the dynamical laws, but approaching them from a different direction. And so this is a conjecture at the level of constructors, and it's actually reality for universal computers. So I expect the conjecture to be true. And it's really something counterintuitive, and it's something that is not yet accepted universally within physics. I think you will find some physicists who are unhappy about this fact because they tend to regard the physics of the heat engines or the physics of universal computers as something that isn't really of concern for physics. But it seems to me this is not a good approach. I think it seems to me they are misguided. So in fact, by studying, as I said earlier, the universal computers repertoire, the universal quantum computers repertoire, we have understood better quantum theory itself. And my bet is that we will understand physics better by understanding the universal constructors repertoire. So that's the third, paradigm shift that's brought about by constructor theory if it works.
A while back, you mentioned something along the lines of the physics of mind. Were you referring to consciousness when you said that?
Yes. So I so I think there's a very strong recently there's been a very strong push for um, for the for the artificial intelligence type of studies. Okay, we've had also Nobel Prizes in physics awarded for studies in that direction and so on. My view is that some of the progress in that direction is progress in the sense of it's there are some studies that are developing some they're optimizing certain things in this area, But it's a bit misguiding, in my view, to frame that as something that allows us to understand how the mind works. So, in my view, it's largely still an open problem, how to emulate the functioning of the mind with a computer. It seems to me that the way in which humans think is very different from some of these optimization algorithms that are being used to solve certain specific tasks. And also, there are some unanswered questions to do with, how do we come up with, for example, a new theory. That's something that we only have some descriptive understanding of. We can also maybe describe at the functional level what's happening with currents in the brain where someone is thinking about a new idea. But obviously that's not, it's a bit like describing some object that's falling down from a tower versus having an understanding of the laws of gravitation, which are obviously much more powerful, and they provide a deeper explanation of what's going on. So to cut a long story short, I think we don't have yet the equivalent of the laws of gravitation in the case of the mind, but there are such laws, and I think they are fully within physics. I don't think this is anything that cannot be described or emulated by a computer, and that cannot be described within physics. So my hope is that we can find a way to use constructor theory, or constructor theory coupled with other methodologies that should be developed urgently, I would say, within physics, to describe the physics of the mind. Why is that important? I think it's important because we want to. It's ultimately relevant, from the point of view of our survival. It's a very important question. How do we come up with new knowledge that can help us solve problems? That's something that it's a vital issue. And so having a scientific understanding of this question, and an understanding that's not mechanical but it's explanatory, is important, because then we could manage to harness new tools to create new knowledge, and this would power up our civilization and allow us to flourish in more ways than we have done so far. And then from the fundamental point of view, which is what actually motivates me, is that it is a beautiful question, and it has a number of very promising aspects to it. So the fact that it will augment the way in which we understand information theory by adding a class of algorithms to those that we already have, which can indeed emulate fully the thinking of a creative human being. That is just one would want to know what kind of symmetries these algorithms might have, what sort of, how do you describe them mathematically, what features do they have at the level of even at the level of computer science. I think this would be a very interesting question. So I think these are very, very interesting questions, both at the foundational level as well as also they are relevant for us, but as humanity in a broader sense. But I think we lack the tools to address these questions, and we strayed away from the explanatory type approach to these issues, which maybe was motivating people like Turing, people like von Neumann, and now we are more like trying to find maybe fine-tuning some specific algorithms to optimize given tasks, the solution of given tasks. But we don't have the conceptual tools to address this bigger question, in my opinion. And so I think physicists, computer scientists, and mathematicians, and philosophers should all congregate to solve these issues. Neuroscientists as well. We should all congregate to try to address this issue at the more foundational level. And I'm hoping constructor theory can provide some of these conceptual tools, specifically because it moves away from the standard paradigm in dynamical laws, which doesn't really even allow you to ask the question, what is consciousness? What is it that makes us different from a given algorithm that is running on any of these ChatGPTs or whatever engines that we are using nowadays?
I also think that consciousness, the entire the entire thing about understanding consciousness as a
Yes.
phenomena is the equivalent towards, or the equivalent to, the theory of everything in the universal context. Like what we are able to do with current computational algorithms and computational methods is mimic or emulate certain aspects of the brain or the human mind, but a, a framework that is able to connect all those singular algorithms into one and work and make them work coherently in a sustainable manner is what we are lacking, and what we need to do in order to completely a understand consciousness, and b, when we do that, we'll automatically be able to emulate it to a certain degree.
Yes. Yes, that's true, and I think we don't yet have that understanding, and I think the main stumbling block is that we don't have the conceptual tools to describe this problem properly.
So, what I was saying was, you very brilliantly touched upon the aspect of how there is a significant need of interdisciplinary collaboration. And that
Yes.
brings me to talk about something a little along these lines, but more about the workflow of your research. As a researcher, when you are working upon something new, novel, or unconventional, at least, what is your approach towards facing that particular challenge, and how does your in general research flow look like?
Um, I so when I'm at my when research works at its best, of course we are. I have to say there's a preamble that I have to place in front of this answer, which is that nowadays researchers are bogged down by a number of things that occur in between research and what you would like to do, which is research, and what you actually have to do. This involves applying for grants and dealing with a number of administrative tasks that have nothing to do with research. If you're a student, sometimes as PhD student, you have to deal with all sorts of examinations that they are imposed on you without any reason, that got nothing to do with your research for the thesis, and yet you are disturbed by. So I think there are a number of things that come within you doing your job as a researcher, and you'd like to do research, but most of the times you're kind of distracted. But when you're not distracted by these things, at least in my case, I really try to follow this problem oriented philosophy, which is just comes natural. It's not that I'm doing it on purpose, but if I look at what I'm doing, it does look like that. You have a problem, and often this problem cuts across different disciplines. I think naturally, well, in quantum information theory, I think you naturally have to study a little bit of computer science and a little bit of mathematics in the direction of logic and so on, and then a lot of physics as well, because you have to understand quantum physics. Um, I come from the physics direction, but I think I had to try to learn some of these other aspects, which was natural in a way. So, because if you study these things in a problem-oriented way, you will find yourself digging for information in all sorts of sources, and then trying to read up to the point where you understand, and to the point that it's useful for your problem, and then you will abandon the thing once you decided that that's not relevant for you want to solve. So my workflow really starts with a problem, and then this problem leads me to a number of things. Most of the times these things are within physics, but sometimes they also go into different disciplines. And I think that's part of the beauty of this work that I'm doing. It's really that it has this aspect of interdisciplinarity. And I think I was also lucky to have available some people that I could ask things to. So, like other colleagues, some people work in different departments. Sometimes, if you have friends that work in those fields, it's really useful to just you know uh, try to sort of pick the brains and try to ask to say, hey, do you know about this particular branch of whatever, I don't know, algebra or whatever, whatnot, whatever is useful for your problem, functional analysis. And then you do find some helpful mathematician that can tell you exactly the bit of mathematics that you need. So it's really a bit like going for a walk in a forest, and you're sort of looking for something specifically, but along the way you notice various things are useful, and then you pick them up, and so you end up having like a basket full of various things. Most of them are useful, sometimes they're not useful, but they're just interesting. So I really think it's reminds me a bit of what very young children do when they're playing with a number of different toys. They play with them for a little bit and they discard them and they try something else. And how long you stay on a given problem depends on how interesting it is, I would say. And But I think this idea that it's really problem oriented, and you don't have to study a whole full course on, as I said, functional analysis to solve a given problem. You might only need a little bit of it. I think that's how I approach things at this level. Obviously, you have some knowledge, which is the background knowledge that you acquired in your previous studies, but once you have a certain level, you manage to sort of add some small bits of expertise to whatever you know already, and that's enough to bring you to the level to solve the problem in question. But definitely, it would be nice to have to capitalize on this possibility of having, for example, virtual connections, these ones that we use a lot during the pandemic and lockdowns, to connect with researchers that are not necessarily in your area, but they may be really interested in the same problems. And I'd like universities to use, to universities and research institutes to capitalize more on this fact, to encourage this interdisciplinary research, because lots of problems that are currently unsolved are unsolved because maybe they cut across different disciplines, and people from each of the disciplines can't quite approach them in their full form, and so that's why the problems remain unsolved. Whereas it would be nice to have more dialogue between different disciplines to try to solve these problems. Consciousness is a problem of this kind for sure. It's one of those problems that require a lot of cross discipline talking.
I think this entire aspect of collaborating with people from other domains and fields would only increase with the advent, and more so the scale at which artificial intelligence and AI tools primarily are growing. Because
Yeah.
right now, is do you use AI in your workflow to any extent?
No, I don't. I know of some colleagues, even some students that do, but I don't, because my most of my work is really, well, I mean, of course I'm using search engines, which, okay, they're not, they don't classify as such, but I think you do look for information over the internet, and I think that's certainly something that can be augmented by an artificial intelligence tool. At present I don't need it, but I can imagine maybe using it in the future. But other than that, I think my work is really, I usually just do analytical calculations with pen and paper, old fashioned stuff like that. So I think that's all I do. And writing, I just write, I just write papers. I don't need to write in a super refined way. So in a way, it's just some bland physics prose.
No,
um,
I think the utilization of AI will be more beneficial to you in
yeah.
the more mundane tasks of, as you said, maybe things related to asking for funds, or targeting
Oh,
that,
yeah, absolutely.
which organizations might be able to provide that fund to you or cater to your specific research.
Yes, I have some friends who are actually using ChatGPT to to refine their some of these prose that you have to write for, and I think that's actually a very useful thing, because it liberates your creativity for something else. Absolutely, yeah. I try to avoid applying for grants as much as I can, but I think when I really have to, probably that would be a good a good tool to turn to, really,
No,
to cut the times. Yeah.
because right, you are right about that. That work like yours particularly requires a lot of how do you say that? Um, Individual.
uninterrupted.
Yeah,
Yes,
uninterrupted, but novelty of the human mind,
yes,
which sometimes, at least at present, would not be really possible with AI, right? Because even chat gpt, it sort of acts as a disruption or distraction of sorts. Because I believe
yes, absolutely.
when you're formulating something unique and truly ingenuine, you'd need that personal room, personal headspace, where it's only you and the
Yes,
problem and a pen and paper, right?
yes, exactly.
But okay, what would be your advice or anecdote of sorts that the young researchers can imbibe in their workflow and research in general?
Sorry, say again. I missed the last bit. There was again some interruption. Can you repeat the question?
Yes. What sort of advice would you give to young researchers, and any anecdote of sorts that they can imbibe in their day-to-day process of research and workflow?
Um, I I think it's really important to have this uninterrupted time where you're just thinking and looking at the clouds, metaphorically speaking. So you really need to have during the day. This is very rare when you grow up further. So if you like you're a fully grown up researcher, you will have lots of interruptions. But as a student, especially as a PhD student, if you can, um, maybe say no to some invitations to go to some networking event or some conferences or something. It just find some time to go for a walk and just think about your problems, or sit at the desk and just wait for inspiration to strike. Sometimes where you're alone and you're just with your problem, that the problem that you want to solve. I think this is really invaluable. I have a friend called Albert Wenger who wrote an interesting book called The World After Capital, and I think one of the aspects that he's touching on, it's an economics book. I think it's kind of saying that attention is now a form of it's really in demand for in the world, in the sense that people don't have time to devote attention to things, and it's become like almost like it's got a monetary value to it. It's something that's really hard to find. And so if you are a researcher, especially early career researcher, I guess, but even later, you need to guard your time to give attention to the problems you want to solve. That's one aspect. And the other aspect is to try not to follow the too much the fashions. So I think if you have an interest, follow that interest, even if it doesn't appear to be fashionable. I know this is something that my supervisor was obviously trying to advise me to be very wise and have some small project that it's something that you can manage, and it's something that is also easy to sell. It's something that can be easily published and so on. So that's good advice. I think if you want to be wise, you can always have a small project of that kind on the side. That's something that will deliver some results easily, and it's maybe not so groundbreaking, but it's still worth publishing. So that's certainly useful. But don't devote every bit of your time to things like that. You should have a lot of your time devoted to what you really like, because the only way to do research properly, in my view, is to do it wholeheartedly, devoting yourself to it for fun, because you like it. That's the only way that creative work can be done, and this is true in any field. And so and even if it turns out that what you do is maybe uninteresting to most people, at least while you did it, you had fun. If you do something only because you want people to be interested in the end, but you don't enjoy it, that's something that's not worth doing, and you will become very upset if at some point fashion changes and the stuff you did is no longer fashionable. So just follow your fear, follow your intuition for what is interesting. And sometimes, you can strike some new fashion. Maybe you open up a new fashion. You can open up a new field like that. So you have more chances to be original as well if you just dig in your own direction rather than following something that's set by others. So this is very important. Don't get too attracted by various voices that you can hear about what's important to to research on. um, Devote some time to genuinely new stuff that you find interesting and follow your heart in that, nothing else.
Oh, wonderful. I love it. But as this this final segment that we do on the show, Dr. Marletto, what is your word to humanity at large?
Oh wow, that's actually, maybe not so different from what I just said. So, I think in an ideal world, um, there should be more people that have time to do creative work. Now, this isn't necessarily in science or physics specifically. For my case, I would choose physics, but any kind of creative work that is done through thinking, largely, is something that makes people happy, and happier people usually are uh, more productive. They are more inclined to be kind to each other. There are all sorts of spin-offs of being happy that help with interactions between between people and make them get on better and so on. So, I'm hoping that humanity can, you know considering that there are lots of very urgent problems, but I think one important thing that humanity should try to enhance is this, um, love for creative intellectual things. And this is something that we should particularly cultivate in children and young adults as well. Not to lose that love for learning that you have as a natural thing when you're a toddler, and then gradually somehow this is lost in most cases. I'm really hoping humanity can find a way not to lose it and to keep it forever for the rest of one's life. I think that's something that, we don't have a recipe for how to do that. I don't know how to instill interest in a teenager for something, or even in a younger child. This should come from within, but we should find ways of preserving this love for learning, the love for creative activities throughout people's life. And so I'm hoping we find more ways to liberate time for people to do that. So instead of having to do, activities that are related to, making a living and dealing with mundane tasks, we can actually make more time for thinking. And then, hopefully some of these ideas, other than being, delivering beautiful works of art, etc., might be even useful for our own survival. So that's actually a good thing for humanity in general. So yeah, really cultivate love for learning and love for culture and knowledge. I think this is something that we really need, especially these days when there are lots of problems creeping up over the horizon.
Dr. Chiara Marletto, thank you so very much for this conversation. It was a delight. It was wonderful. Thank you so much.
Thank you so much for having me. It was delight to have the conversation as well. Thank you.